Hello again. Same place, but it's a few hours later. Gonna go over the exercises for 6.3 and 6.4, and then I'll discuss some more things we can do with truth table analysis in 6.5 and 6.6. And then on Tuesday, November 5th, I'll be back in the classroom and we'll talk more about a lot of these things and answer any questions that have kind of added up or you didn't ask about in the meantime. So definitely do keep some questions available if you have any. But hopefully you're reading the text, you're following what I'm talking about here, and it's making sense as you kind of work through the truth table analysis. It's almost like like a computer code. It's just sort of rule following. If you follow the rules and know what you plug in at that point, then it's pretty automatic as to what answer you'll get. You'll see some more of that today. So anyways, on to the review of the exercises. So first one was exercises 6.3, exercise section 1. This is on page 361. So I assigned 1 through 10. And so you use truth tables to determine whether these statements are tautologous, self-contradictory, or contingent. So you do the truth tables for the propositions here. So in the first one, you have just one, so it's 2 true or false options, and then you work out the truth table, and what you'll find is that it's all true under the first horseshoe. That's the main operator. And if it's all true, then it's tautologous. So the answer to 1 is tautologous. And then if it's contingent, that means there's a mixture of true and false, and if it's all false, it's self-contradictory. So that was basically what you do on 1 through 10. And so number 2, the answer is contingent. Number 3, the answer is self-contradictory. Number 4, the answer is contingent. Number 5, the answer is self-contradictory. Number 6, the answer is tautologous. Number 7, the answer is tautologous. Number 8, the answer is contingent. Number 9, the answer is contingent. And number 10, the answer is self-contradictory. So if I were in class, I'd probably go over a few of these. And if anyone has any questions, you just couldn't get the right answer, send me a picture of what you did, and then I could send you a picture back of how it should look, and then maybe hopefully you can see, aha, that's where I went wrong. But if you're careful and plug in the truth values right and get the functions down right, then it should get the correct answer. Section 2 was comparing statements. And remember, you had 4 options there: logically equivalent, contradictory, consistent, and inconsistent. So what did I assign here? 1 through 15 odd. So number 1 is logically equivalent. Number 3 is consistent. Number 4 is logically equivalent. Number 5 is logically equivalent, sorry. Number 7 is consistent. Number 9 is logically equivalent. Number 11 is contradictory. Number 13 is logically equivalent. And number 15 is contradictory. So we had one of each of the 4 in those answers. Again, if you're wanting some extra practice, you can do some of the evens. And there were some that had the answers at the back of the book, or you could ask me and I can tell you what the correct answer was. So that was it for 6.3. And 6.4, that's when we really started doing truth tables in terms of arguments. So in what I assigned, 6.4 is 1 through 10. And you're to use truth tables of these arguments to determine whether they're valid or invalid. So remember, if you do the truth table of all the proposition lines, and if there's a line where the premises are true and the conclusion is false, then you know it's invalid. If there is no such line, then it's valid. Okay, so we'll give the answers to the 10 here. I did basically an example of one in class. No, it wasn't one. Actually, yeah. Modus tollens is the example of one. Number one is a argument called a modus tollens form of argument, which is one of the valid forms, which we'll talk about today. And so you will have done truth tables to show that it is indeed a valid form of argument. So one is valid. Two is invalid. Three is valid. Four is valid. Five is invalid. Six is valid. Seven is invalid. Eight is invalid. Nine is valid. And 10 is invalid. So that was it for the homework that I assigned. So today now, this is the lecture that would have been covered on October 31st, Halloween. So I'm missing whatever costumes some of you are wearing. I am in London. They don't do much Halloween there. So I won't be seeing many costumes around London unless things have changed. So 6.5, start talking about that. Indirect truth table. So the basic theme in this section is basically shortcuts, right? So one of the things that you've noticed in some of the arguments that we analyzed in terms of determining whether they are valid or not is that in an argument that had three propositions, it was 8 lines. So you had to go through 8 lines to determine whether it was valid or not. If you had 4, suddenly you're up to 16 lines to determine whether it's valid or not. And 5, you'd be up to 32 lines. Now you could do that. And again, like a computer, it's pretty routine and mechanical. And a computer could do it really, really fast for you. But for you to do it, you would have to do 32 lines, all the truth values of all the lines, and then look to see if there's a line where the premises are true and the conclusion is false to determine whether it's invalid. And then if there are no lines like that, then know whether it's valid. So the indirect truth table method is basically a shortcut. And so that's what that's the main thing that we will learn from this section. And on page 372, it talks about preliminary skills. And the reason for this is that one of the key things about an indirect truth table is that basically what you try to do is you try to show that you can make the conclusion false and all the premises true. If you can't do that, then it's valid. If you can do that, then it's invalid. So basically you don't go through this difficulty, or not the difficulty, but the tedium of going through 32 lines or however many it will happen to be to come to that conclusion. You just go straight to trying to make the conclusion false and the premises true. And so one of the preliminary skills, as Hurley refers to it in the textbook here, is as we think about some of these truth functions, we can get locked in to certain truth values for the proposition. So take behind me A dot B. So if we take A dot B, and if we're told that, let's say we wanted to make that as one of the premises true, we know that A dot B, and A conjunction B, is only true when both A and B are true. So if that's going to end up being true, then both A and B have to be true. Now, if it needed to be false, then either A or B can be true or false. They just can't both be true. One has to be false. So you have a couple options there. So sometimes it takes a couple steps to find out whether you can turn something into an invalid argument or not, but this is one of the ways in which it works. And a true implies false statement. That's kind of easy one. You'll be happy when you see those, because if, for instance, let's say this is the conclusion, and you have all these premises before, as we'll see here, this is an argument that I'm going to look at in just a minute. When you have an implication like this, and you want it to be false if you're going to show it's invalid, then you know that this has to be true and that has to be false. Right? That's the only circumstance that makes it false. Any other, it's true. This is kind of confusing to have true false here, but let's say A implies B. Okay, so if the only time A implies B becomes a false statement is when A is true and B is false. If B were true, it would be true. If A were false and B false, it would be true. So the only time it becomes false is when the antecedent is true and the consequent is false. So the last one, let's say we want to make A or B true. The only time it is false is when both are false. Any other time it's true. So as you can see, that's another one of those circumstances where you're going to have to perhaps go at it a few times before you can determine whether it's invalid or not. So now let me go on to the text, and I want to read the paragraph in Hurley. This is on page 373. So as with the last lecture, it will be helpful to have your textbook with you so as we go through this together, and I'll kind of explain what's going on and have this example on the board. So he says, to construct an indirect truth table for an argument, we begin by assuming that the argument is invalid. That is, we assume that it is possible for the premises to be true and the conclusion false. Truth values corresponding to the true premises and false conclusion are entered beneath the main operators for the premises and conclusion. Then, working backward, the truth values of the separate components are derived. If no contradiction is obtained in the process, this means that it is indeed possible for the premises to be true and the conclusion false, as originally assumed. So the argument is therefore invalid. If, however, and this is a key point, and I'll talk about this in a second, if, however, the attempt to make the premises true and the conclusion false necessarily leads to a contradiction, it is not possible for the premises to be true and the conclusion false. So in other words, while trying to make a premise true, you can't. It always becomes false when it needs to be a particular value. Then you can't turn it into a true premise, and therefore you can't make the premises true and the conclusion false. So you can't prove it's invalid. Why? Because it's valid. So that would be how that would work. We'll look at a couple examples of that to show you. It'll be in the textbook. But let me go through this argument just to show how we would go about doing this. So the main operator, see, this is the first premise before that first line. And so the main operator is this horseshoe, so we want to make this true. Okay? And then the not B is this, it's a premise all by itself. We want to make that true as well. So we can already fill in what we know B needs to be, because B needs to be false in order for the negation sign to make it true, right? B will be false. The negation sign makes it true. Okay? So B is false. So we can put false here under B. Okay? And then we know C implies A. This is the conclusion. If this is going to be an invalid argument, the conclusion needs to be false. And so that means that C has to be true and A has to be false in order to make the implication false. Okay? So far there's no contradiction. So we now know that C has to be true and A has to be false. So if A is false, plug it in here, but it becomes true because of the negation sign, and C is true, which makes this true, which makes that true. So we could make the premises true and the conclusion false. Right? In the B or C here, it is only false when it's F or F. But we don't have F or F, we have F or T. So therefore, the whole thing becomes true. And true is the antecedent, so we have true implies true, which makes the whole implication true. And then under the B, it was true. And then we have the false conclusion. So we have true premises and a false conclusion, so therefore we have an invalid argument. So you can see that's called the indirect truth table method. You basically kind of just assume you can make it invalid and then go from there. And if you can, then you've shown it's invalid. Sometimes it doesn't work that way. So I'm going to look in the textbook, the example that they give at the top of 375. Okay, so you'll notice they have not A implies B as the first premise. And if you don't have the textbook, then kind of write this down. Not A implies B. B implies A. A implies not B. And the conclusion A and not B. So basically, this is the proof that we're looking at. This is the argument. So not A implies B, B implies A implies not B, and A conjunction not B. So as you can see, the A under A and not B, we want to make that false. There's three ways to make that false. With A true and B true, with A false and B false, and with A false and B true. So there's three ways of going about making the conclusion false. We obviously don't want a situation where the conclusion's true, because that's not what proving an invalid argument would entail. So that's why we start, remember what it said, you go backwards. So you start with the conclusion. That's why it was so easy here. Once we started going backwards, we knew that the C had to be true and the A had to be false. And so then you go back through the rest of the propositions and the rest of the premises and you fill in those truth values, because you know that's what it has to be if it's going to be an invalid argument. So we have 3 lines to work with. So it's still, I mean, it's not as much of a shortcut as it would have been if we had 4, but sometimes it works out a lot easier than this. And this would be helpful if it was like several propositions too. So we go back and we try to make the premises true. And so we have to assume in these 3 lines that we will have true premises, right? That's what they have here. Under the 3 horseshoes, there, and there, it's true. So how do we get that? So working backwards again, the A implies not B. With the first line, we had B is true, and then it becomes false by the negation sign, and then A is true, but it's supposed to be true, but true implies false is not true. It's false. So we can't make that premise true because it becomes false in that line. Okay. So what about the next line? Okay. So the next line turns out we can make it true with those truth values. But if you look at the first one, that not A implies B, you end up with true implies false. That's supposed to be true, but true implies false is false. So you can't make that first premise true. Okay. So what about the third line? And do the same thing with the third line. You can make the third premise true. You can make the first premise true. But if you go to the second premise, you'll see that you can't make the second premise true. You end up with true implies false again, which is not true. It becomes false. So as you see then, this you can't make the conclusion false and the premises true. So what does that mean? It means it's a valid argument. So there'll be some exercises like that to determine whether arguments are valid or invalid. And it's just really a matter of, and in fact, it'd probably be easier to use this indirect truth table method because it is such a shortcut that gets you the answer more quickly. So the other thing we can do with these truth table shortcuts is some of the other things that we were doing with arguments in the previous sections about consistency. So on page 376, it talks about testing statements for consistency. So remember, statements are consistent if there's a line where they're all true. This is a handy one to be able to use the indirect method for, because there could be some propositions or some arguments or statements where I have 6 or 7 propositions, and you end up with a huge truth table analysis if you did the full thing. So if you'll look, for instance, at the statements that are listed at the bottom left of 376, these statements here. What they have done underneath is simply to assume that they are true. And and actually this is probably a good one to write up. Okay, so got it all up there. So A or B, we want that to be true. B implies C or A. Want all that to be true. And C implies not B. We want all that to be true. And we want not A to be true. So we now know that A needs to be false, because once it gets negated, it is true. So if C is going to be true, then what do we have? Let's go false or true. Then it would be true. Let's see here. B implies this needs to be true. So what do we have? C. A is false. So this has to be, B is true. So to make this true, this has to be true. Okay? Right? Because if this were false, then that whole thing would be false. C or A would be false if both C and A were false, which would make this implication true implies false, false. So C has to be true, and that. So then if we go on and put the C value here as true, and this needs to be true, then B needs to be false. But as we've seen already, we were forced to make B true. So that makes B is true, which makes it false. And so we can't turn it into true. So it's not consistent statements. So that's a way of using these truth tables to determine whether statements are consistent or inconsistent. Okay. So that finishes section 6.5. The exercises that we're going to do, and I'll kind of explain these. So when possible, compute the truth values of the simple components in the following compound propositions. If no truth value can be computed, write a question mark under the letter of or letters of with the unknown truth value. I'm assigning 2 through 20 even. I'll do 2 and 4 in right here, and then kind of give you the sense of what I'm looking for. So 2 says Q implies N, and you want it to be true. Well, there's many ways to make that true. It could be true implies true, false implies true, false implies false. So we can't know which truth value for both of them. So it's unknown for both. Okay, so that would be the answer for that one. 4, we have N implies G. We're told the whole thing is true and that G is true. But if N were true or false, it would still result in being true. So the N is unknown. It's unknown there. Let me do 6, since we already had 2 examples of that. So 6 would be K and B. K, and the conjunction has to be true. Both have to be true for a conjunction to be true. So you kind of like conjunctions because you kind of know which ones have to be true. They both have to be true. So K and B both have to be true. So that's the basic exercise for that. And I said 2 through 20 even. Section 2 is you use indirect truth tables to determine whether the following arguments are invalid. So you basically take an argument like on 1, B implies C, then negative, not C, and then not B, right? An argument like that. And you put it into something like that as an argument and do the truth tables to determine whether it's valid or invalid. I've assigned 1 through 7. And then section 3, it's comparing statements. Are they determine whether they're consistent or inconsistent? What did I say? 1 through 5 there. So again, try to make all propositions true in terms of determining whether they're consistent or inconsistent. Okay. Final section today, final online section. From here on out, I'll be back in the classroom. Section 6.6 is argument forms and fallacies. So one of the things that I have said before is that logic is all about the form of the argument. It's not so much about the content of what is being said, whether what is said is true or false. That's for science and other disciplines to determine the truth value of things. But assuming the truth value then, and the arguments based upon true propositions, or what are taken to be true propositions and statements, what are the valid or invalid forms? So we now know through the truth table analysis the ways in which we can prove whether an argument is valid. And one of the things that has come up in logic is that there are several forms that are thought to always be valid. And so I'm going to go over these. The first is, I'll do it 2 at a time, modus ponens and modus tollens. So modus ponens and modus tollens, it's most common logical form, and basically the way our textbook has it out is it's modus ponens is P implies Q, P therefore Q. So if you were to do a truth table analysis of P implies Q, P and Q, you wouldn't be able to make the premises true and the conclusion false. So it would be a valid form. The next one is modus tollens. This is another valid form of argument. I put the MT here because that's sort of the form that will be used as you start doing proofs. You'll just be writing MP, MT, right? That becomes the custom or the convention for the rule. These are often called the rules of inference, meaning anytime you have these two premises, you can conclude this by this valid form of argument or rule of inference, right? So if anywhere in a proof, we haven't gotten to proofs yet, but we'll get there. If anywhere in a proof we have a P implies Q and a not Q, then we can say not P, right? Because we know that with these premises on hand, we can conclude this. That's what these logical forms tell us, right? That's saying that that's a valid conclusion you can always make. Because we're now moving to propositional symbolic logic, so we're not talking about the statements that those letters correspond to. We're just talking about the letters in their symbolic form right now. So that's the first two. Second two are pure hypothetical syllogism, referred to as HS. P implies Q, Q implies R, P implies R. So if you pass this class, then you will graduate. If you graduate, then you'll get that great job. So if you pass this class, then you'll get that great job. So that's filling in the letters with statements. Again, we're not delving into statements anymore. We're just dealing with the symbols at this point for the propositions. So that's yet another valid rule of inference or valid argument form. The other is what's called a disjunctive syllogism. DS, P, or Q. Where do they have it there? Not P, therefore Q. So it's all in the text. I'm on page 384 now, but if for DS just stands for disjunctive syllogism. So either you pass or you fail. You didn't fail, therefore you didn't pass, right? That would be, wait. You either pass or you fail. You didn't fail, therefore you passed. Right? That would be the disjunctive syllogism. Okay. All right, 5 and 6. Five is called constructive dilemma. It's a more complicated argument. I have to write these on the board separately. So one way to think about it, if you get cats, then you'll have fleas, and if you get dogs, then you'll have smelly house. Either cat or okay, sorry. Either if you get, so another way to think about it, if you get a cat, then you'll have fleas, and if you get a dog, then you'll have smelly house. Either a cat or a dog, therefore either fleas or a smelly house. So that's basically the constructive dilemma. That's CD. Now it might look like a complicated one. Why did they come up with that one? It's actually something that's not an uncommon argument form that emerges in debates. You kind of see the example I gave about cats and dogs. It's kind of a real world context where you might see an argument like that being put forth. The last of the argument forms we're going to look at is what's called destructive dilemma, very similar to this. It is DD instead of make sure I'm getting it right. P implies Q and implies S, not Q. Okay, So it's kind of, you can see why it's kind of destructive lemma. It's sort of very similar form, but it's taking the negations. So again, if cat, then fleas, and if dog, then smelly house. Neither, not fleas nor smelly house, therefore not cat or dog. Okay, so another way, it's basically kind of saying in the one, if you get this, this will happen. If you get neither, neither will happen. So I guess another way of saying that. Okay, so then they go on to talk about the two invalid argument forms. We've talked about these a fair bit. But it's worth kind of processing this and kind of remembering this. The one is affirming the consequent. P implies Q, P, no. This is probably the argument you've heard the most in this class, affirming the consequent, or AC. A consequent is what follows the implication sign. So if P, then Q, Q, therefore P. That's an invalid argument form. You could do that on the truth tables and see that it's an invalid argument form. The one we've looked at, and you probably already have it in your mind, is if you study, then you'll pass. You passed, therefore you studied. So you can, not only can you imagine a scenario where the premises are true and the conclusion false, but doing a truth table analysis, you can logically show and prove that you can have the premises true and a conclusion false. So that's affirming the consequent. The other one is denying the antecedent, referred to here as DA. So if P implies Q, and if the antecedent is P, and we're denying the antecedent, we're saying not P, therefore not Q. Again, I think we've talked about this one, using the same example. If you study, then you'll pass. You didn't study, therefore you didn't pass. Again, for similar reasons, you can imagine a case where you didn't study but still passed. And not only can you imagine that situation in a real-world context, logically you can prove that you can have true premises and a false conclusion there. So those are the two common fallacies, logical fallacies. So I think that brings me pretty much to the end of what I want to talk about today. And what we will do next week or on Tuesday when I get back is we will, let me go over the exercises that I'm assigning here and talk a little bit about that, but that'll get you ready and going. And and then on class, we will talk about this more, and we'll go over this again next class if it's still not clear. Because now we're really starting to get into true logic, or what people today would consider true logic. So 6.6, all I have you doing is 1 through 15 odd. So let me do the first 1 and 3, just to kind of show you. As it says, interpret the following symbolized arguments in light of the 8 argument forms presented in this section. In some cases, a symbolized argument must be rewritten using commutativity or double negation before it becomes an instance of one of these forms. I'll talk more about that in class on Tuesday. But for the most part, use the 6 rules that I just went over to determine whether these are valid or invalid. So, for instance, we have N implies not C at number 1. All right. N implies not C, therefore not N. That is a valid argument form. It's modus tollens, right? So it doesn't really matter what letters here, right? In the argument form, it uses P implies Q, not Q, therefore not P. But anything can be in the place. In fact, as we'll see as we get into other proofs, you can have whole compound statements in the P spot and other compound statements in the Q spot. And if the negation of the consequent statement is in one of the other premises, you can then have the negation of the whole compound statement in the P spot. So it doesn't really matter what goes into the P or Q spots. It's all about the form of the argument. So in that case, it's a valid argument form, modus tollens. And for number 3, A or not Z. And then it says not Z, therefore A. Now it might look like that's valid, but the reason it's not valid is because not Z is simply the same as not Z. In order for it to be, again, you would have to be not Z, right? It'd have to be, you'd have to negate the not Z in order for it to be the negation of that, right? Because the rule is P or Q, not Q, therefore A. So that's why it's not in the valid form. So that would, the answer to number 3 would be invalid. So that's the basic idea for these. I've assigned 1 through 15 odd, and that should cover it for this week while I am out of town. So I will see you all in class next Tuesday. I hope you all have a great weekend, and I'll see you on Election Day, November 5th. Take care.